All right, so homework 5 is out. Yes, I keep belting you at this succession of homeworks, but don't worry, it lets up in the next part of the semester. And as we hit you, therapy consists of beating the patient with a whip or something like that. All right, so and I should soon be running some results for you about how your test cases did. That I have a little coverage tool that I'm updating to the new syntax that basically goes through basically takes a solution, a parser that I've written, and runs your programs through it, your test programs, and sees how much of the parser gets exercised, how many rules get called, and it's kind of a tool like this that is kind of fun. It's basically the Bison equivalent, Bison/Horn equivalent of a coverage tool that you may have encountered out there in the real world that tests to see which statements you have not in your program you have not tested. All right, that's a bug. All right, and you can submit them by a bug submit, and it's probably, sometimes you'll get a response on Piazza, but it's okay. You can post that on the bulletin board, but really I'd prefer, I'm not going to respond to any more questions about why my program, or what is it, a life lesson that from me to you, and it's all meant for your, let's see, where were we? Oh yes, we were doing this precedent stuff, going through this exercise of looking at the machinery underneath, when in fact you won't really have to look at the machinery underneath because there's a tool to do it for you, is in part so that to help you with diagnosis. And also because I just think as a general rule, it's never good to be, maybe there's some Amish in me or something like that. I don't believe in using things that I don't understand. So here we are. This is an example of what happens when you write an ambiguous grammar, such as the E star E, and therefore there's going to be ambiguity in that grammar as written about whether star and plus are left or right associative and what their precedences are. So the way that shows up, if you look at the machines that get generated, what are called LR machines, what you'll see is that they have states. They'll say you can get yourself into a situation. What this means, to read this off in English, you can get yourself into a situation where you have just seen an E plus, that's the top line there, you've just seen an E and a plus, and the next symbol, at that point, you then see another E. You will then be in this state over here, where you've seen an E plus an E, and you've also seen, of course, because you've just seen an E, you've also seen this E right here in the second line, and this E right here. This is in state 6, for those of you who are listening. The second line and third line, which tell you that you could be looking at a plus or a times at this point in a valid string. But it also says the first item there at the top says, well, we're at the end of a right-hand side that could be a handle that could be the thing that we ought to be reducing to E. And if the next symbol is a star or a plus, then that is a valid thing that you could do. That is, there are sentences in this language where the right thing to do at this point is to convert the E plus E into an E. Or a right thing to do is to convert the E plus E into an E. All right, well, that's fine, but that means, of course, that we don't know whether we should be actually taking that reduction or whether we should follow the lead of, we see, for example, a star or plus, or whether we should be following the lead of these other two things and going to a state that says that we're going to put off reducing until we get the far end until we get to something like an end of file or a parenthesis or something. So that's the difference between left associative and right associative. It's the difference between grouping. It's the difference between giving plus precedence or giving star precedence. And the little trick in this particular problem comes up quite a bit when you're dealing with expressions, and the classical technique is to write them out as lists. So to say you have an expression is a list of terms separated by pluses and minuses. A term is a list of factors separated by stars and slashes, etc., etc. And that unambiguously tells you what to do. But it's tedious. So you can write things in a much clearer fashion, the way that in fact they are written in they are often written in reference manuals. They say, well, you have all these operators, and here are their precedences. So you can do that. All you have to do is come up with a way of saying what is the precedence of the operator. And the trick in Bison and Horn, a very cute little trick, is to say, okay, well, we'll just assign operators, we'll assign each operator a precedence, and we'll assign the productions that they are part of a precedence depending on the operator, and on the basis of the relative precedence of those two, we'll decide what to do. And that's exactly what happens here. So if I want to give star higher precedence than plus, then or if I want star to group more strongly, then I simply give it higher precedence. And the rule that Bison will follow is, oh, well, in this conflict here, where I don't know whether to shift to this star or go up there, I will choose to shift the star. I'm sorry, I'll choose to shift the star on the grounds that the thing behind me is an E plus E, and I should actually combine that last E with the next, with the star in the next E before I group in the E in front of that. So by just juggling these around a little bit, you can get all of the usual effects of operator precedence, which is really very cute, if somewhat confusing. Now, this is additional information that you have to add to the information that you get from running the algorithm that produces this table, because the algorithm works on the grammar only, and the grammar doesn't say. Yes.
So in your
Yes.
lower down the list, the higher precedence.
Yes, that's right. Well, that's just the convention in Bison. I mean, it's not as if this is a great principle that the lower precedences are higher. It's just that that's the way that Bison and Horn do it. Yes.
Does Bison handle precedence by changing the DSA that it uses to parse?
Yes. I'm sorry. No. Yes, I see what you're saying. Yes. Actually, it does. What happens is that in a state like this one, let's consider that state up there at the top. What it's going to do is to say that. No, that's actually an interesting question. Wait a minute. Let me hang on. Let me rerun in my mind exactly how it accomplishes this. Let's see. In this particular case, it would. Oh, I see. Yes, it just changes. That's right. It changes the table. So the table entry for here simply tells it the table entry for star in state 6 will say shift. Will say go to whatever the next state is, that the E star dot state, and the table entry for plus will say reduce by the E plus E entry. In fact, there's an exercise in the next homework where you play around with these tables. So we can use the same thing for the famous dangling else, because here the problem is that you want that second else to group. You want that second else to group with any inner then, rather than So what that means is that we simply give else higher precedence than then. And so when we come to an else, so that when we come to that else, we know that we are supposed to reduce this. We are supposed to keep shifting it rather than immediately reducing. So if then, else, the else will group with the second if then and not with the outermost if then. So you can use it with if then else. However, I must warn you again, I've done this before, I must warn you again that this is dangerous if you try to extend it beyond expressions, unless you know what you're doing. Now I sometimes do it, but then I know what I'm doing. So, and even then it doesn't work all the time. So it's best to just use this mechanism for precedence. It's a very elegant mechanism, but it does have quite severe limitations. Okay, so there you go. That's the problem. Now then we come to these other things, these reduce-reduce conflicts. Sometimes you can have a situation where there are two reductions, two possible reductions in the same state. That means that you have an item set that contains two reductions, that is, two things with the dot on the far end of the reduction, meaning at this point you could do this reduction. And the look-ahead symbol, and they share a look-ahead symbol, which says, okay, if you have an A, then you can either, at this point, you can either make the preceding alpha symbols on the stack into an X, or you can make the preceding beta symbols on the stack into a Y. By the way, test of understanding, advanced test of understanding. What can you say about, can alpha and beta be anything? They mean, alpha and beta in our convention means some string of symbols, string of non-terminals and terminal symbols, such as appear on the right-hand side of a grammar rule. So could they be anything, just anything? Or alternatively, can you come up with something that they can't, a combination of alpha and beta that's not possible? Epsilon would always be fine. Any thoughts? Yeah.
I think that the ending characters of alpha and beta should be the same.
That's right, because this thing means, the meaning of the dot is that we've just seen all the stuff on the left. So that means that either alpha has to be a suffix of beta or beta has to be a suffix of alpha. Otherwise, it means that you're in trouble. Otherwise, it means that you got to this state by two entirely different means. You don't know. The state does not reliably describe what's to the left of the dot, and that's not good. Now, these reduce conflicts generally mean that you've done something naughty. It's usually well, there are exceptions. In fact, there are exceptions in the current homework, in the current project. But usually it means that something bad has happened and with your grammar. And there is no, you can't fix this with precedence rules because it's not a conflict between, well, you could give one rule precedence over the other, but it doesn't have quite the same meaning as you might expect, because for one thing, usually you will be called upon to make that decision sometime after the place where the error actually occurred, and that's not particularly good. So there's not much to say about this except that you have to examine the grammar and figure out why this sort of thing is going wrong. So here's an example of a sentence which can consist either of an empty string or a bunch of identifiers. And the problem is it can be a sentence, a single identifier, or a bunch of identifiers. So that's redundant, obviously, because you could just say epsilon or IDS. But if I throw in an extra ID, then I have a problem, because at the very beginning of a bunch of IDs, I don't know whether I should think that there's an epsilon there, or whether I should put an ID there. So either one is possible, and I'm not sure which one it should be. So I don't know whether to take the epsilon. Well, now wait a minute. That's not good. This is a shift reduce. Oh, I see. If I have an ID and an S, then I don't know whether I should produce at that point a second epsilon. Well, the way that they show up in the DFA is like this. You'll see two sets. You'll see the dots at the right over there, and that tells you that we have problems. So I could either have an empty S and put an epsilon there, or if I've already seen an ID and if I've already seen an ID and an S at this point, I can reduce that, and it's a wash which one you should do. So and the thing to do is, in this case, it's obvious that you simply rewrite the grammar, but in any case, you will generally see a problem manifest itself like this in your grammar. Now there is definitely a case in Python where the reduce-reduce conflict occurs, and it's kind of where it naturally occurs if you follow the grammar. From the book, and there's a good question about how you should do this, and that is that the left-hand side of an assignment can be is a list of identifiers. It can be a list of targets, basically, and so there are things that can be targets, that can be the targets of an assignment, and there are expressions that can't be. And the problem is that you don't know until you get to the equal sign which you're doing. So you don't know whether x plus y comma z, if you have a statement that starts that way, which is, strangely enough, a valid statement, x plus y comma z. You don't know whether that is invalid or whether it's a valid list of expressions. You don't know whether x comma y, whether the x is intended to be an identifier whose value you're taking, or if it's intended to be the target of an assignment. So if you write your grammar in the obvious way, you will get these reduce-reduce conflicts, where the thing tells you, I'm not sure whether I'm building up a list of targets or a list of expressions. You can deal with this in two ways. You can rewrite the grammar. You can make everything be expressions, and simply check the tree afterwards to make sure that you haven't accidentally allowed the guy to write x plus y equals 3. Or you can use our fancy GLR parser, and GLR parser deals with this kind of problem by trying both reductions, and only one will ultimately work. And so it will eventually find this out and throw away the failing production. Well, more on this at some later time, but right now let's go on for this. So Bison by default produces a machine like this. It tries to optimize it a bit by, as this thing says, if you have two states that differ only in the look-ahead symbols for some of their reductions, then those states are compressed together into a single state, and that saves space. Of course, these days saving space isn't so important, really, and the parser is not really a big part of the execution time of the program. So these days, Bison has some additional modes that are largely irrelevant to us here, but they allow you to build fuller tables that have more of these entries in them. And that's probably so you are free to use those particular declarations, but I'm going to leave it to you to find them. And I very much doubt that they're going to make any difference in your program. So here we are. This is what we. This is where we stand here all together. A diagram that I've blatantly stolen from one of my fellow graduate students at Carnegie Mellon years ago, and in his book on compilers. So what we have is this sort of Venn diagram of grammars. You have the LL grammars, which are the top-down, the things that you can parse with recursive descent, and then you have the bottom-up grammars, the LR grammars. So let me explain what these mean. LL0, the 0 and 1s refer to, or things in parentheses, refer to the number of symbols ahead you look. So LL0 means that I can always decide what to do next without looking at any symbols in the input, without looking at the next symbol in the input. Now, if you can always decide what to do next without looking at the next symbol in the input, what does that tell you? Yeah. Very uninteresting. Yes, in fact, it has I think it means that you can only accept one string or something like that because it always has to know what to do next. So that's not very interesting. LL1 is the usual recursive descent where we look one character ahead. We look at the next character and decide what to do. And LLK is you can look some fixed number of characters k ahead and decide what to do. There's also an LL. There turns out to be another category, LL star, which means where you scan ahead to see if such and such a character exists anywhere. That's perhaps that's interesting, and you'll find it in Antler, for example, but we haven't talked about it here. Then on the LR side, we have LR0. Now, LR0 means that you, on the basis of what you have seen, on the basis of what you've scanned so far, you decide what to do, and you don't have to look ahead at all. So this is actually not a small, this is not really a tiny grammar. It's actually somewhat substantial, and but it's not very useful for our purposes. So you can come up with examples where this works. And in fact, the interesting thing is you can actually turn any LL1 or LR1 or LRK grammar into an LR0 grammar. The problem is that in so doing, you mess up you make it difficult to write semantic actions that make any sense. So that's an interesting. I'll leave that out there for you as a challenge, but it's not a challenge that's terribly important. So I'm not going to go into it. Now SLR is something we haven't talked about. It should be SLR1. Something we haven't talked about. It's a technique that used to be taught. That I used to teach, I guess, many years ago, but I've stopped because I don't think anyone uses it. It's basically you take LR and to get the look-ahead sets, you use follow. So instead of there was this method of finding look-ahead sets by if you go back and look through the notes, it's by basically moving them from one item to the next. Instead, what this does is when you come to a possible reduction, you figure out whether to take the reduction by looking at the follow set of the thing that you're about to produce. So you have A goes to foo plus bar, and the look-ahead set is then the follow set of A. So that's sort of like, it's sort of a mixture, if you will, of what you do for LL1 and LR. And then you have LR1 is what Bison by default does. That's the LR construction, except we collapse some of the tables. And then you have the LR series, LR1 and LRK. These are all unambiguous and, in fact, deterministic grammars. There's an additional, and these are all contained, I should say, inside a larger class, which is the class of all unambiguous grammars. There are some unambiguous grammars that you can't parse by these methods because they basically require you to, in effect, they require you to guess what reductions to take, and but only one set of guesses will ever work. So they're unambiguous, but you can't figure, by looking just one symbol ahead or a fixed number of symbols ahead, you can't figure out which reduction is going to work. So they're unambiguous, but they're not in this category, which is the category of deterministic grammars. And then finally, you have the even bigger class, the ambiguous grammars over here, which aren't covered at all, except for those you need Early's algorithm. So Early's algorithm will take this whole thing at the cost of speed, and otherwise we try to limit. So for programming purposes, we generally try to limit ourselves to either about here, this one here, or this one here. So that's what we've done, and that leaves us with. So this is basically the idea. So we're wrapping up parsing at this point. So all of those hard 172 type exercises that you've been getting, they come to an end with homework 5. Well, they don't come to an end actually because there are tests, but never mind. In the homework they come to an end. So this is basically the idea here. The big idea is, or big ideas are, I write in a sort of a specialized language, BNF, I write a description of what I'm trying to accomplish, namely the conversion of a string of characters, the conversion of a string of tokens into something that indicates its internal structure. A tree that indicates its internal structure or something of that sort. And I'm driving that translation by taking the description of the grammar and producing from it, automatically, a converter, a translator, that drives, or something that drives the translation actions. So we can do this by a number of ways. We can treat the grammar as a recursive program and write a recursive descent parser. We can treat it as we can do the same thing except encode the recursive. Instead of writing the recursive descent parser out, we can actually summarize it in a table. That gives us LL1. We can do things bottom up, which has the advantage of not making decisions until you have all the data, until you have more data, and that gives us the LR family. We sometimes we can put little efficiency hacks, although they don't usually make a difference in what you can do. So that gives you Bison. And then we have a very general algorithm that will do this for any grammar, and that is used only in very specialized cases. Like, for example, grading homework 4, I used Early's algorithm. Well, that's because you can put your denullifier into, you can give it grammars that are ambiguous, and you want the thing to still work. And we can get the same effect as Early's algorithm in Bison, or largely the same effect, by throwing in that GLR parser option, which basically says that when there's an ambiguity, try everything, try all possibilities. You will later discover that some of them die out, and otherwise you will discover that 2 of them survive, in which case you know you've got an ambiguity. So, and these are your tools that you're using in Project 1, and this is sort of the big idea from this section of the set of big ideas from this section of the course. All right, I'll take questions, but we're going to take a break, and then I'm going to look a little bit. We'll talk a little bit about practicalities, like practicalities in diagnosing grammar problems and that sort of thing, which you are about to run into in spades if you haven't already. All right? and maybe a few words about the project as well. Okay, so let's take a break. No, that's not what I meant to do. There's the green one. Wrong color button. Yeah. Uh-huh.
I submitted my on this grammar, the prefix suffix one, my start state appeared on the right side or something. But when I actually run it, it doesn't appear on the right side anymore. That's my start state, and it doesn't show up anywhere else.
Uh-huh. So this was the input to your... Wait,
This was the test that it failed on. The, at least that's what the thing
I don't know. You'll have to bug submit it, so I'll take a look at it. I don't know what that's all about.
Sort of thing I should bug submit.
Yes.
All right. Okay. Thank you.
Yeah. Okay, let's take a look at some of actual grammars here. This is in there was a directory of files supplied back with Lecture 10 that contains this. Here is a simple, I believe, unproblematic grammar, sort of typical thing for doing plus and star. And when you run this, I believe it works. And what you find, if you ask Bison nicely, it will produce this file, gram1.output, that contains, and this, by the way, Horn does this whether you ask it nicely or not. It always does this, produces a .output file, which contains a copy of your grammar. That's useful to look at, by the way, because sometimes your formatting is confusing in your actual file, and you aren't really quite aware of what grammar the thing has accepted. So it's good to go here. Now, when you do this with Horn, you will see a bunch of symbols that start with underscores that have been introduced behind your back. They start with underscores because you're not allowed to use those symbols. You're not allowed to put such symbols in the context-free grammar. And it uses those symbols for the purpose of handling the star and the plus and the question mark operators and a few other and parenthesized things and stuff like that. Okay, so here you have the grammar. It gives you a list of all the terminal symbols that you've got down here, which is sometimes useful, and all the non-terminal symbols. Gives you a cross-reference. And then it gives you the state machine, and here it is. State 0, state 1, and so forth. The only problem with this is that it thinks that you're really that you are lacking for real estate for file space for the output files. So when you look at this, you will find that it doesn't. Excuse me. It doesn't include any of the items that have a dot at the beginning, except for this one, except for the very top one. But never mind that. You can figure out what those are supposedly. Is the idea. So what this tells me is what in each state, what my states are. State 0 is the initial state, and it tells me what I should do if I see an ID in a parenthesis and all that sort of business. So what should I do if I see an expr term or primary. So it tells me either that I should shift, or it tells me, and where it says go to, that's sort of like shift, but for a non-terminal. And then down here, where I find something, yes, right here, for example, where I see something, a dot on the far right, that tells me that if I see a star, I should shift, and if I see anything else, I should convert that term into an expr. So that's pretty straightforward. That's the idea here. And as I say, the problem with this, a potential problem with this is that, for example, when you get to this state here, you'll notice that there's an expr plus a dot and a term. There's also, as you know, if you've been following, there should be a bunch of productions for term. Term gets something or other with a dot in front of them. But this doesn't. But since it's assumed that you understand that there are supposed to be those things, it doesn't tell you about them, which is kind of annoying. But there you go. All right. So so there you go. That's the state. Let's take a look at another example. I think there's a problematic one here. Let's look at one with a problem in it, like for example, gram 2. Gram 2 is an ambiguous grammar. So this is a pure ambiguous grammar, and as we've seen in the lecture slides, this tells us that there are states with conflicts in them, and we can go down and look at the conflict and diagnose it. So state 9 has a conflict, and it says that the conflict here is that when it sees a plus, it can shift, or it can reduce according to the rule for expr. And it's put this in brackets to tell you that by default, Bison has just decided to do plus, but it doesn't. But it's just doing that at random. It doesn't know that that's necessarily the right thing to do. Now let's look at. Let me try to find a grammar that's. I think there's a. Let's see if gram 3.y is in there. So this is one where we have supplied precedence to disambiguate the grammar, and the result of that is that we get this nice output, and in the problematic state, like state 9, for example, where there was a problem before, now there isn't a problem. It says. It sees a dot plus, and it sees a plus at the end. And when it sees a when it sees a star, it's going to, a star at this point, it's simply going to do a reduction. It's decided to do a reduction. I don't know why it doesn't have the, why does it not have the shift for plus? That's kind of strange. I don't know what that's all about. So if we go to see, now some of these are interesting because they have grammars because, yes, here's a typo. There's a typo in this grammar, and the rule for term. So what exactly is the typo in this grammar? This is a very common typo, by the way. Many of you, at least a substantial fraction of you, will make exactly this error. Yes? Yes, there's an extra epsilon for term. And that's going to cause problems because, well, it's just going to cause problems. I mean, that's not what we intended. And it shows, and this is going to show up as gram4.output. It's going to show up as conflicts galore. So even in the very first state, it says it doesn't know down here. Well, wait a minute. That's the grammar. Where's the state? All right, here we are. Even in the very first state, it tells us that if it sees anything, it's going to, by default, it's going to reduce using a term, which is ridiculous because at the very beginning it doesn't have a term. So we know immediately there's a problem. And you can, and in this case, you can conveniently go back and look at the grammar, and it tells you, and it makes the empty rule that you accidentally inserted plain by putting an empty there. So that's kind of useful. Well, you can go and explore this and see what kinds of errors you get for each of the different kinds of errors that you can put, or messages that you get for each of the different errors that you put in. So I'm a little bit curious. Let me just ask this question of you in your projects. How many people are trying to build how many teams are trying to build a tree and then print the tree? And how many people are doing this by building up a string? Those are the two strategies. Okay. Tree, raise your hands. String, raise your hands. Really? Well, I've got questions about people wanting to know how to... There were questions on the Piazza board about how should I concatenate things together. What happened to you? Did you have an epiphany or something? I mean, what was it? No? Okay, well, all right, since nobody volunteered that they're doing strings, let me say that the rest of you who made trees, I think you made a good choice. So with that, you can now take off and enjoy your weekend.